This talk for today is reserved for the platinum partners of this year's conference, HTech, who have significantly contributed to achieving everything we envisioned. This is another milestone in our long-standing collaboration, and we hope there will be many more. So, next we have Milan Stankic, Senior Engineering and Delivery Lead at HTech. Milan will be presenting optimization of AI inference, the role of ML compiler, and hardware innovations. In this session, he will explore how machine learning compilers and hardware advancements are transforming AI inference, particularly for LLMs. Milan will discuss strategies for optimizing performance, addressing challenges like high computational demands and leveraging specialized hardware such as GPUs, NPUs, and custom accelerators. Please welcome Milan Stankic to the stage.
Hello, everyone. My name is Milan Stankic, and I'm a Senior Engineering and Delivery Lead at HT Group. Besides that, I'm also the member of ML Compiler team. And today, I would like to give the answers on some of these questions, like why we actually need ML compilers, what are the ML compilers, how they are built, and in last few sections, I would like to cover how this LLM era, let's say, or hardware innovations make our job more challenging, and also how we actually can fit everything in memory and execute at all. So, on the beginning, let's talk about the compiler, or particularly ML compiler. So, main goal of compiler is to enable AI model execution. Like you have some model that is created in PyTorch, TensorFlow, or some other framework, and you want to execute that on some specific hardware. So, you need to translate your ML model to pretty much binary code that can be executed on hardware. And that is not the only task. So let's say that you are able to compile model, get binaries, but if you don't have a good performance, or you don't have a good resource utilization on your hardware, that will be useless. So you will not get your response in some reasonable time, or you will use a lot of resources, so it can be quite expensive. Another thing that also compiler needs to enable is effective deployment. Like you need to provide some results that are accurate enough that you can use that, so they can be useful for you. And another thing is that reliability. So without your compiler and your entire system should perform well, even if you have some high load. And actually, two more things that I want to mention why I think that this talk is important and inference is important. Grok CEO, so that is the one company that is making AI hardware now, a few years ago said that around 80% of the model in Google that are already trained and almost ready for production, they are just dropped because of high estimated cost during the execution. So they invested the time and money, and they just decided to drop. So it was not efficient, and also there was quite expensive. Also, another thing that I want to mention now, that there are some estimates that if you take into account total cost for your model training and also model execution, up to 90% can be spent only on inference time. So that is important that we reduce the cost on that side. And now, what is a compiler? So in some high-level definition could be that compiler is some tool that translates high-level language into low-level code that can be executed on hardware. Here we have examples, some hello world written in C, we have compiler, and we get a binary file at the end. So with ML compiler, we have pretty much the same thing. Now, input is model that you create in some of the ML frameworks, and goal of the compiler is to produce binary file. Now, where all of those ML models are executed, one aspect that we want to check is actual hardware. So besides these CPU and GPUs, like traditional hardware that are already was even present there before this ML or AI hype, also there was a GPUs, FPGAs in that moment. So those are the hardware that you can probably run your models. But in last several years, we are getting ML models are executed on pretty much everything. So we have also the rise of different custom AI hardwares. And I will talk about that in a couple of minutes. And now if we are talking about use cases or domain or where the actual models are executed, we can talk about data centers, laptops, mobile devices, cars, also some low power devices that, for example, should be always on, listening something and producing some outputs to you. This second part of this slide is important just to understand how different you can have requirements for your compiler and for your hardware. If you are targeting some data centers, you will probably need to have very small latency, very good performance over there. On the other side, and also you can probably have some bigger power consumption. On the other side, you can have wearables like watch, or you can have mobile phones. You don't want that your hardware that is running something in background just drain your battery. So in those cases, power consumption will probably be more important, or at least equally important as inference that you get from that device. Now, if you're talking about complexity that is in front of ML compiler and ML compiler team who is working on that, there is different high-level frameworks. Like, as I mentioned, PyTorch and TensorFlow, but there are several more frameworks. And if you are building compiler, you have a goal to support all of them. Also, if your company is creating hardware, so you are in semiconductor industry, you want to enable running all of those models in your hardware. So that's the one thing that make this compiler work complex. Another thing is that the number of operators that you can have in different frameworks. For example, in PyTorch, you have more than 500 operators. And if you take into account different overloads of those functions, like you have different data types, you have different parameters, in PyTorch that can go to up to 2K parameters. So we need to have support for all of those parameters. And if you compare PyTorch and TensorFlow, even some of those operators has the same names, they can have similar attributes, and they can behave slightly different. So that is another thing, that you need to create some common set of operators and address all of those differences between different frameworks. And the last thing is actually quite big number of different platforms where you can deploy your model. I believe that if not in the past, you will probably have a need to deploy your model to mobile phones, to laptops, or to some data centers. And if we combine all of these factors, we can have some matrix like is shown on right side. We can have multiple frameworks with fully support, like for in most of the cases, all of those frameworks will work on CPU. On GPU, you can have partially supported operators or not, or even you will not have support for different frameworks. The good thing, if you buy some, let's say, NVIDIA GPU or AMD GPU, or even if you buy some specialized hardware, there is a big chance that all of those different frameworks will work on your machine. But also, it will be good before you start with creating model or even planning to deploy model, just to check basically how mature is support on that specific use case. I want to mention one thing here. In HTech, we had several teams who are working on mobile domain, and they are building applications that should be executed on let's say Android and iOS devices, and those guys share with us that they have a lot of rework. So even they create one model that in theory should be easily moved to another device. There are still low usability between, basically reusability between those platforms. And how compile, well, I'm not quite sure how compilation works. There is some problem, but I will try to just rephrase. So in most of the compilers, we can identify three parts like front end, middle, and the back end. Those are responsible for loading your model, make some transformation or optimization over there. And at the end, you have a back end that you'll need to generate the code for your platform. And the problem with multiple different languages and multiple hardware platforms was already resolved like 20 years ago. So this is the structure of LLVM compiler. LLM stands for low level virtual machine. And that is, I would say, a well-known compiler that you can, on input side, you can have a C, C++, Go, Rust, Code, Swift, etc. And you can produce the execution executable to different platforms. So the same thing is now just reused. So that problem was resolved, as I said, 20 years ago. So in ML compiler, we can have similar structure. First part is commonly named model loader. So we will load the model, or just representation of your graph that you created, and maybe perform some optimizations over there. There are some set of platform-independent optimizations, like those are coming from math, like if you can make some graph rewrites, replace one node with another, but keeping the semantic, and apply some optimizations in, let's say, ML domain. One example it can be on the left side. So this entire subgraph is group norm operator. So in my compiler, if we recognize this pattern, we can tell, okay, this is group norm, and just proceed with compilation and just reduce entire processing. Or just we will not waste too much cycles and transfer data over there if we recognize that this is group norm. Now I would like to list just a few frameworks and languages that are commonly used for compiler development. So it's unlikely that you will start from the scratch. TVM is the first project. It also has their own intermediate representation, and you pretty much get complete stack. You are able to load different models and produce some code that can be executed on GPUs, CPUs, and also a lot of custom accelerators. Another project is MLIR that is also mentioned in previous talk. It refers to multi-level intermediate representations, so that can be treated as a subset, or also rely on LLVM IR. So the main idea here is to get more expression, like comparing to regular compilers that will compile C or C++ code. Now you can introduce the concept of tensors or tensor operations, and basically you can have a different level of abstractions. Another thing is Triton, so that's a framework, and also some DSL that is used for, initially was targeting only GPUs, but now you can target different platforms. The one thing that Triton was trying to resolve is the huge gap between PyTorch, ML, like those ML frameworks, and something that is low level and related to performance optimizations. As I said before, if you start with your PyTorch model, you will write probably some Python code. But what will happen if you want to make something with your data within the graph, but you cannot express that? Like you want to introduce new custom operator, and there is a huge problem in that moment. So if you want to have a performant code, you will need to insert CUDA code. So it's unlikely that you will have in one person someone who is writing, is maybe coming from data science, writing all of those models, working on training the models, that he is very, very good in CUDA, and he can write some kernels over there. So Triton has one idea, just to provide some framework on some custom DSL where you can express what you want in some Python-like language, and the compiler and all other things will be hidden from user, and you will get code that is performant. Another very similar project to Triton is named Mojo, and the reason why I put this here is that the same guy who actually created the Mojo is the guy who created MLIR and guy who created LLVM-IR. So they showed some results, like comparing to NumPy running on machine, they are 37,000 times faster. So you can probably not imagine how fast that can be. So this is also one promising project that I want to mention today. And one more important thing, all of those projects are open sourced, or most of those parts of projects are open sourced. And also HTech has a contribution in many of those frameworks right now. We have teams who are working on those compilers. And now if you're talking about optimizations and you had to deploy your model to some edge device or mobile device, and also in previous talk there was some of the things are mentioned here. Quantization is technique where you basically try to compress the weights of your model. You can compress the weights and also activations over there. Accuracy is a downside of that, so maybe you would like to execute some of the layers like normalization in the FP16 just to keep the precision for those nodes. In most of the compilers now support that you can somehow express which nodes to execute in a lower or higher precision. There are also the frameworks where you can, even before you deploy your model, you can make a test, like mark some nodes that you want to execute in different precisions and get basically verify how results looks like, and basically continue from that. Weight-only compression is enabled in some of the compilers. Like I already have trained models, let's say that weights are FP32, but with this flag I can tell compiler, let's compress those weights. This is very important for reducing the memory footprint or your entire model, and the cost of that is decompression that needs to happen, or dequantization that needs to happen in runtime. I will talk briefly about that. Pruning is another technique where you can just remove some of the layers from your model without too accuracy lost. Sparsity is another thing that will, I would say, be more important in the future. With different activation functions, in some cases you can have a lot of zeros or values that are very close to zeros across the tensors. And if you can identify those, you can pretty much compress the weights, compress the activations. And right now you can also find on the market some hardware that actually supports this sparsity over there. So it will give a lot of benefits. AVQ stands for Activation Aware Weight Quantization. That is also another thing that you can produce a model with like 4 bits weights, and during the execution we can just dequantize those weights and proceed. And what actually happened in this compiler work when LLMs are introduced? So the one important thing that I want to mention is this curve that shows the sizes of ML models. There are some also discussion that maybe this can saturate in one moment, but right now you have a lot of data. Let's say that we are talking about Llama 270B. You have 70 billion parameters that can be tuned. It's around, let's say, 240 gigabytes of data. And you have device like you have 32 gigabytes of RAM. So now you can imagine how complex that can be. So if you want to produce one output token, you need to load 240 gigabytes and pass through your hardware, and you will need to get some result over there. Also, the good thing that right now for Llama, for example, you will have 3 different versions of models. So with basically this model size can be different. And some of the techniques that I mentioned before can help a lot. And this diagram on the left side is probably more important that you spot in last few years. It is from paper Attention is All You Need, and shows the architecture of transformer. Now, while I'm mentioning here, so there are two big, at least two parts of this transformer architecture. It's encoder and decoder. They're also named prefill and decode. And now if you have some hardware and you saw the numbers like tera operations per second or something like that, so that I will show you that that is not so important, like that particular number with some explanation. Another metric that you can maybe hear for these LLMs is number of tokens per second. We have two different stages in prefill and decode, and they can be quite different. So I would like to mention also some metrics that are shown on the right side. Like time to first token is the time that basically until you get first response from your model. You enter the entire prompt, hit the enter, and in prefill, we will process all of the tokens that you enter. There are different parts of that encoder architecture, and you will get response back. Now, and time per output token is the time until after that you will getting one by one token. So some of these metrics can be quite different. Like if you are building some chatbot, response of, I don't know, time to first token of 3 seconds is probably not acceptable to you. But if you provide some huge file and tell the LLM, let's summarize this, you can probably wait like 10 seconds. Also, another thing, that the speed of the reading for adult person is around 240 words per minute, so it's like 200 milliseconds per word that you need. So in some cases, if you have one-shot prompt, getting the tokens like in the speed of 200 milliseconds is quite good. So you cannot read faster than that. And also one more thing on this slide. So this first part named prefill is compute bound. So we will process all the full prompt that we got from the user, and the rest and the code part is memory bound. Like we need to read all weights and just to get single token. And how we can improve that. So Kiwi cache optimizations is one thing that can help. In attention, you will have query key and value matrices. So that is something that is written in this paper. And if you go to decode phase, you will need all data that is processed in prefill plus every single token that you provided on the output. So instead of recomputing everything for every single decode phase, you can probably have one prefill and like 8K decode phases. You can just try to cache at least some of the parts of the pre-calculated or intermediate results and just reuse that. So this Kiwi caching is one example of that. And also now one important thing to mention here is that the Kiwi cache size will limit the number of batches that you can execute at the same time. So the memory consumption can be significant here. So that's a second problem. So first problem with memory is that you will have huge models. You need to do something with them. We need to compress and make another tricks. Another thing that if you want to have good performance, you need to cache values, and also you need to find some optimal value. For this Kiwi cache part, there are different techniques how to do that. Sliding window is one idea, like I don't need to cache everything, just cache some of the values that is present in some of the Mistral models. Another thing that can also improve this decoding part is named speculative decoding. And the idea behind this, do I really need 70 billion parameters to read to get an answer what is the capital city of US? Probably not. Maybe some small model can just produce that and predict what big model will generate. So the idea here is that small model can run 5 times, 6 times, n times before you actually run once this big model. And big model needs to just reject or accept some of the results that are generated by small model. In order to implement this, you will need to use the same tokenizers, otherwise models will not understand each other. And also you'll need to have very fast runtime. So you'll need as fast as possible just to switch between different models. And another thing that maybe you can also stumble across is related to model architectures or something that is named hardware-software co-design. So on these 3 pictures, you can have the structure of GPT-2, Llama 2, and Llama 3 models. And you can see that they're pretty much the same, but there are some tiny differences that also can help in basically getting the better performance over there. One example is a normalization operator. So in layer norm is replaced with TRMS norm. That helped with training is a little bit faster, and also you have more stable convergence at the end. And also in runtime, there are few less cycles, let's say. Another thing that is GLU that was previously used is replaced with SILU activation functions that also will reduce slightly the number of operations that you need to execute. Now, I would like to talk about AI accelerators. I mentioned accelerators on the left side. On the right side, there are some acronyms that you maybe already recognize, but maybe you will hear about them in the future. NPU stands for Neural Processing Unit, but also this TPU can be treated with the same goal. So we want to build specialized hardware that will have a good parallelization like GPUs, that will have, we will just drop the complexity that you have right now in regular CPUs, and we want to have low power consumption and also enable running like int4, int8 data types over there. VPU, APU, and DPU are some extensions that you can find. Even right now, you can find them next to your CPU that are responsible for some virtual or some video processing or data processing over there. Just a few years ago, this was the, let's say, common architecture in deep learning. That is some vision model, and 90% of all computation was done in convolution. So in that moment, you just had to, if you want to improve your hardware, you will add extra arithmetic or logical units and make matrix multiplication much faster. Right now, since we talked about huge memory consumption and the boundaries that are added in decode, something has to be changed or improved. So this is quite old picture that shows the data movement cost, at least this for energy part, but also if we just append the numbers, how much cycles do you actually need to reach to get your data from DRAM or from some buffer that is not next to your accelerator. You'll figure out that getting the data from memory or writing back to memory is main bottleneck with LLMs. So one thing that popped up in the last several years, and I would say in last year is maybe more important, is this in-memory compute. So let's say that we have some memory units, we put weights over there, and we just added some tiny hardware over there that can perform multiplication and addition over there. And if you just write what is happening on those wires, like if this is input, output is on the left side, on the bottom side, basically we have a matrix vector multiplication. So this is the one thing that right now there are several different companies that are creating something that is called digital in-memory compute that will significantly reduce the overhead. Like data is already there, we just need to multiply and add. Grok is one company that is in this AI part, and that is, I'd say, important from one perspective, that they try to simplify the hardware as much as possible. They make a memory just flat, and compiler is responsible for taking care about every single processing unit. So entire work, or all operators are mapped to like 10 different operations. And right now, everything is memory. On every single cycle, they reprogram entire network. And this gave like 80 terabytes per second for memory bandwidth. So this is the reason why this Grok has a very good performance results. And one company goes one step further. They say, instead of just traditional architecture, let's make single chip, single wafer that can store entire like Llama 270B model on the single chip. And the results are here. Like, this is a snapshot, maybe 1 month ago, or maybe just a few. I don't mention the date, but I want to emphasize this. So 136 output tokens per second is the best GPU solution in that moment. And at the same time, they have a 2K output tokens per second. So it means that in 1 second, this hardware will generate 4 pages of text. Like Hobbit will be generated in less than a minute. And now you can wonder, why is that important? As earlier I mentioned that you can read with like 200 milliseconds to read one single word. But this will enable agentic AI. Like, you will be able to run model multiple times, and you will get a response to your user like in 1 second. But in the background, you can run that 10 or 1,000 times. And one thing that is also recognized is that we have both scale up and scale out. If we have one processing unit, let's scale to make single device, put all device together. And with this approach, you can have solutions that put everything in memory, like all 70B, like 240 gigabytes of weights you can put in single system. One thing that also need to be mentioned here, that you need to have a very efficient communication if you want to scale. So this is something that a lot of different companies are building right now. Why this heterogeneous computing is important? Right now, you can go to shop and buy laptop with NPU, and this is, as I mentioned, dedicated hardware for your PC. Why is that important? You can offload some tasks to NPU, like in this example, some segmentation can be done on NPU, and after that, you can just use a GPU for the rest of the activities. So this trend will enable making AI-first applications. So you, as a developer, will rely on some hardware that is already present. You can offload your entire work, so development of AI applications will be much easier. And the last thing that I want to mention for today, right now we have a diversity of AI models, and we also have diversity of use cases. Like I mentioned, data centers, where we are getting 2K tokens per second, but we also have mobile phones that we don't want to dry our battery. And everything will probably move into some circles, like different use cases will require different hardware, and you will get new models in this hardware software co-design, and you will just continue with innovations. So that's all from my side. I hope that you, I think that we can stop now.